When I'm looking at the curves that we were looking at on Wednesday and yesterday, where my equations are now in terms of my parameter t, I have different kinds of derivatives that I can take. Let's consider this set of parametric equations. Do me a favor and graph this. Let me pick a range of t's. Let's get a picture. What shape do you get from this? Leo? Sideways parabola. We've seen this one. We did this one on Wednesday. We had an equation for this x in terms of y, right? When we worked it out, we did the elimination of parameter. We figured out an equation for this. If I want the slope of a tangent line at any point on this curve, I need dy dx. And so the real question is, how do I find that slope? I hope I have a weird answer.
So changing t changes where you start looking at the function.
Yes.
So does the function just exist anywhere, any t, and now just start from a different point?
Yes. So if I change this set of t's, then the piece of the curve I'm looking at starts someplace different. If I ignore the t altogether, then I'm basically saying use all possible values of t from minus infinity to infinity. That would describe the curve in its entirety.
So it does have to be.
It has to exist in at least the range I've described it in. There are restrictions, I can use them, but I can also abuse them, right? If one of these was an ln, then I wouldn't be allowed to use negatives. If one of these was a tangent, I'd have places where it was undefined. I'd need to obey the rules for continuity. Which means to do derivatives, I need to take that into account. So that's not an unrelated question. Let's suppose I pick a point. How about t equals 2? We're at this spot. What do you expect the slope of the tangent line to be? Just looking at this graph. Leo?
It looks like it's positive at that point here.
Probably not a very big number since the graph isn't very steep there, but it's probably a positive number. But that's change in y with respect to x, and what I have going on right now, x and y are both in terms of t. Now I could do my elimination of parameter, I could rearrange this. I think that's more of a pain in the ass than it's worth. So I'm going to exploit the chain rule. If I did my elimination of parameter, then y is some function of x. I don't know what it is. And at the moment, I'm going to say, I don't actually care. But in my head, I know that y is actually a function of t, and x is a function of t. So I'm going to write this chain rule. Maddie, you were tutoring this the other day, outside and inside, right? So there's my outside, there's my inside. Capital F, outside function. X of t is the, if I take my derivative with respect to t everywhere, then on the left side, what do I get? That's a function of t, takes derivative, I get y prime, right? Or I could write it dy dt. On the right side, I need the chain rule. Chain rule says you take the derivative of the outside, leave the inside alone. Well, the derivative of the outside, that would be f prime. Or the derivative of f with respect to x, because I left the inside alone. And then I multiply by the derivative of the inside. But y is f of x. That means that this expression right here, that is dy dx. As long as this thing is not 0, I can divide. It's inside alone, right? I leave the inside as x. And all of a sudden, I have a way to figure out what dy dx is without doing the actual elimination of parameter. Holy crap, I can get away with leaving everything in t. With our set of equations, what's dx dt? There.
2t minus 2 is dx.
And then dy dt,
b is 1 because the 1 goes away unless it's 1 over t.
and that means I have an expression for the derivative dy dx with no y's or no x's in it. I have a parametric expression for my derivative. At our point, the one we picked in our picture, I know the t value there. Take that t, plug it in. I didn't need to do my elimination by parameter, elimination of parameter. I could leave everything parametric and I could figure out my slope. Does this jive with our intuition? Remember, we said by looking at the picture, we expected the positive slope, and we expected it not to be a very large number. 1/2 is not very large. That's a shallow tangent line rising as we go from left to right. It works. Here's another point. Slope of the tangent line there. Exactly, because I have a t-value of 0. I put in 0 here, and I get negative 1/2. Does that jive with our intuition? Yes. Now here's an interesting note. When we think of dx dt, we're thinking how x changes as t increases. Remember, on this curve, we're coming up from the bottom and going back out on the top. So dx dt is a negative number. We are going to the left. dy dt is a positive number. We are going up. dy dx is negative, a negative and a positive. But dy dx is always measured from left to right. dx dt and dy dt are measured in the direction t is increasing around our curve. That's the motion on the curve itself. And if I put in a larger range of t's, I see again at 0, that still makes sense. Negative tangent line as we go from left to right is a descending slope. Questions? I did say we were allowed to divide as long as we weren't dividing by 0. So here's a question for you. What happens if dx dt is 0? And if my slope is undefined, what do I know about my tangent line? What kind of a line has an undefined slope? A vertical one. Where is dx dt 0? At t equals 1. And that's where our tangent line is vertical. We have that spot is the vertex of this parabola. The other possibility is that f prime does not exist there. Wait a minute, what sort of things are places on a graph where my derivative is undefined? Ooh, all the way back to Calc 1. But that would be a vertical line, right? A vertical asymptote would be a place where the function wasn't defined. That picture of a bird, right? There's no well-defined limit for a tangent line. When you come in from the right, the slope should be really positive. When you come in from the left, the slope should be really negative. My limit doesn't exist there. Chapter 2, section 7 or 8, the existence of, we did this on pictures on exam 1 last semester in Calc 1. Last year, or whenever the hell you took it. If both dy dt and dx dt are both 0 at the same time, 0 over 0, I might actually have something that works. L'Hopital's rule still applies here. But that means I can actually look at curves that are more complicated looking. I'm not going to give a range of t-values this time. I want to look at this curve everywhere, but it's really only interesting in a small range of t's. So let's leave our t's from -5 to 5 on our calculator. Graph this sucker. I get a loop. Curve crosses over itself because there are two different t-values that give the exact same x and y. Right here at this spot, and by the way, if we hit trace, we see that we are actually coming from the bottom up towards the top. So we're moving to the left. Then we hit the loop and we come down and we start moving back to the right. This makes sense. X is t squared. When x is a big negative number, we're going to get big negatives. And as x gets closer to 0, we're going to get closer to 0. And then when x starts to become positive, we're going to start going back the other way. That's how t squared works. But t cubed means the y values go negative, positive, negative, positive. That's that up and down motion for cubic behavior. Up, down, up. I've got two horizontal tangent lines. How do I know? Yep.
I can see how on that part of the loop where it's flat, above and below.
I have a maximum and a minimum. If I have a maximum, I must have a place where f prime is equal to 0, or where f prime is undefined. F prime is a polynomial. Sorry, y is a polynomial. I should have two places where its derivative is 0. I have a vertical tangent line, where dx dt is 0.
This is really a normal function. Did you integrate just inside the area?
Hold that thought. I'm doing derivatives first. I'll get to integrals in a bit. But that means you can give me the slope at any point here. By the way, you can check that on your calculator. Hit second calculate, the trace button. What do you see right above there? I see dx dt, dy dt, y dx. I have the ability to check my derivatives right there. But wait, there's more. Please give me the expression for dy dx. Put that over here, or will it get washed out? No, it'll work. The reason I write this without primes and I write it with the DDT notation, the Leibniz notation, is because I like to think of the DTs as canceling out. If we were actually writing this as a fraction, the over dt on top, the over dt on bottom, those would cancel. So I get 3t squared minus 3 over 2t. You can now give me the tangent line at any point we want, as long as you can figure out the t value. So if I asked you for the tangent lines, there will be more than one of them here. How would we find those tangent lines? Got to be more than one of them, because we cross that point going up, there'll be a tangent line this way. We cross that point again, a tangent line the other way. How do I figure out the t values for that point?
I think I have to set it with when t value is greater than this, then some that would indicate directionality that we're increasing.
Yes, but I'd have to do that from here, right? I'd have to break that up here. But it's easier than you think, because that sounds like my first derivative test, right? It's increasing, it's decreasing, I find the t sections. That gives me maximum, minimum. I want to find a particular point rather than finding a direction yet. What t value puts me right there? What do you know about the coordinates of that point? Y equals 0. Let's take y and set it equal to 0. So either t is 0 or t squared minus 3 is 0, which gives me t is plus or minus the square root of 3. So if I put in 0 for t, I actually end up over here, because x will also be 0. So the coordinates of this point are when t is negative square root of 3 and when t is positive square root of 3. And now I can figure out two different slopes. When t is negative square root of 3, we'll be coming up curve from bottom to top, going from left to right. I should expect my slope to be negative. When I hit positive square root of 3, going this way, out from left to right, instead of from right to left. So I should expect a positive slope. There we go. And you can find those slopes. Because you can take these two numbers and plug them in here. Still dealing with derivatives. We did the first derivative test, right? We found maximums and minimums by looking where my derivative was 0. By figuring out where it's not 0, I can say, oh, well, the graph is increasing there. Or decreasing there, right? We did something else with derivatives. Part of this graph is concave down. Part of this graph is concave up. What did I use to determine concavity? Second derivative. How do I take a second derivative if this is my first derivative? Well, that's actually another application of the chain rule. because what I want is the derivative with respect to x of the first derivative. But when I'm doing a derivative with respect to x, I'm not just doing it with respect to x, I'm doing it with respect to t. So what I need to do is I need to take the derivative in t of this thing and divide it by dx dt. Just like I took the derivative dy dt and divided by dx dt because I was taking the derivative of y. Well, now I'm taking the derivative of this thing, derivative with respect to t, dx dt. I know how to do that because this is the quotient rule. And we already know what dx dt is. Ta-da! Oops. 2t. Yes, 2t. Unfortunately, means I got to do the quotient rule here. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So on the bottom, I'm going to get a 2t cubed. And on the top, I get 12t squared minus 6t squared plus 6. Please notice, where do we change concavity? I need to know where that's 0 or undefined. It's 0 when the top is 0. When is the top 0? Yeah.
Maybe the top part is 3t squared minus 3 is 0, it could be 0 over the numbers.
Right, but 3t squared plus 3 is never 0. It's something squared plus something. That top is actually never 0. Where's the bottom 0? Only at 0. Which means we change concavity exactly once at t equals 0. This whole part is concave down. This whole part is concave up. So everything I can do with regular ordinary derivatives, I can still do with parametric derivatives. Questions? Yes, David.
I did like a 6t times 2t.
Oh, the derivative of the top times the bottom. The top is 6t, that's gone. Leave the bottom alone. Okay.
Why do you think about the whole thing by dx dt?
Because that would be dy dx ddt. And I'm doing ddx. If I want to do a derivative in x, I need the chain rule again, and that's where this extra piece comes from. It's unfortunate, but every time I do a derivative in x and my expressions are not in x, I need to bring that piece back in. Better? Still is. Concave down, concave up.
Like 2 units ago, did you do
Isn't that what dy dt is?
Yeah, that's like by dx at the bottom with respect to x. Why are we?
Because what's your second derivative? Y double prime. That's d squared y dx squared. It's the second derivative with respect to x. If I switch them and I do the derivative of x with respect to y, then I'm turning my entire picture sideways. I can do that, but it's weirder. More questions? I could do that, and it would be substituted back in. It would be fine. You did ask the Nebi question of the day, though. Integrating. I want the area inside the loop. Where do I find it? I'm going to start with the statement that I think will make your life easier. That loop is symmetric. The top half and the bottom half are the same. So if I find the top half area, I can just multiply by 2. Yes? But let me think about this in general. Way back when we did integrals the very first time, I drew a picture like this, and I said this area is the definite integral f of x dx. But f of x is our equation y equals f of x, right? So if our curve, instead of being described in terms of x, is described parametrically, then when I'm drawing that equation, I'm figuring out this value down here. That's an x value, isn't it? But it will be x of some t value. And this will be x of some other t value. If I think of these pieces, isn't this describing height? That's y. So I could think of this as y dx. So down here, let's do that. We'll do the integral y of t, but then I want dx, like it was a u substitution. Dx dt is the derivative of our x equation, isn't it? So what if I wrote the derivative dt? That is exactly the correct formula to give me this area. Son of a... All right, wait a minute. Right, our graph looks something like this. What were the t-values that put us at this point? Leo?
The answer is square root of 3.
Aha. And our direction for this curve was this way, right? As we drew the curve, as t increased, we came up from the bottom, up past the loop, down around the loop, and up off to the right. So the one I encounter, the t-value that I encounter first is negative square root of 3. And then this point right here was where t equals 0. So if I just want the upper half, what are the limits of my integral? Those would be x limits. I'm looking in t. That would give me the bottom half. When we hit this the first time, we hit it at negative root 3. And then we hit 0. Remember the orientation of our curve. The upper half is bounded from negative root 3 to 0. So if I want to do this integral, those are my limits. You looked like you were going to ask me something, Maddie. I can do the whole thing, but I don't think I need to at this point. I'm just going to multiply by 2.
We're going to do that.
I could go from negative root 3 to positive root 3. That would give me the whole thing, wouldn't it? But let's do it this way for the moment. Y of t, x prime of t, dt. Well, that's actually a relatively easy integral to do, isn't it? I'll take this 2 out front, and then I get t to the 4th minus 3t squared, integrate dt. Okay, I put in 0, I get 0. Minus. I got to cube this thing, I got to fifth power this thing, I'm going to get stuff that sucks. Negative root 3 to the 5th over 5 minus negative root 3 cubed. Yeah. All right, wait a minute. Every time you square the square root, it goes away, right? So do a cube, I square it, and then I do one more. So this is 3 square root 3 with a negative. This is that times another 3. That's 9 square root 3 with a negative over 5. Grab your calculator, tell me what that number is.
-15.5884.
Now add this thing, because minus a minus is a plus, and we get,
10.39.
did you divide by the 5? Now, here's the problem. Everything we've done is correct. What do you notice that's weird about this answer? Why? That's correct. The answer to this integral is a negative number. Why is that right? Give me words. I'm moving from right to left. And is it dx supposed to go from left to right? We're going backwards. So our answer has the wrong sign. That is the correct answer. So here's where you have to know more geometry than our calculus lets us know. You have to know, hey, this area should be positive. Take the absolute value. By the way, I only got the top half. If I want the whole area inside the loop, I need to multiply by 2 again. I believe there's an example in the textbook that uses the arch of our cycloid and asks you to find the area under that. Questions? If our graph is oriented vertically, let me change the picture just to give you something a little different. Let's suppose I had a parametric curve that looked like this. And I want this area. You did these back in chapter 6. How would you do an integral that looked like that? Yeah?
You click on top here, subtract the bottom here.
That would be really, 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 really hard. You could, but it might suck. And I don't want to do it that way. So there's got to be a better way. Not that that's wrong, it's just a much more difficult way. Ready for my sneak? Now I can think of this x as a function of y. And instead of taking the area under the curve, I'm taking the area under the curve sideways. So the little slices, instead of going up and down, are going side to side. If my little slices are going side to side, then their thickness isn't dx anymore. Their thickness is dy. And that means this area is the integral of x dy. If it's the integral of x dy, then in parametric terms, we do x of t times y prime. Same exact idea, turned sideways. So Leo, while you are correct, I could try and find the top curve and the bottom curve and do that. I don't have to. One of those edges is still an axis. By the way, if your area is on the left side, it'll be negative. If we're going from top to bottom, it'll be negative. Your orientation still matters. Questions? Arc length. We used ds, right? And we had two different versions of ds. 1 plus f prime of x squared dx, and one was 1 plus g prime of y squared dy. Well, what if I wanted to do this in t? If you go back to the arc length discussion we had in class, we actually started with the distance formula. And the distance formula is change in x squared plus change in y squared. So I actually get to write it like this. And that actually is so much nicer, because the distance formula is right there in the middle of the damn equation. And that's how we built arc length, was by using the distance on the arc. And that means this works not just for arc length, it works for surfaces where we did the integral with the ds in it, 2 pi x or 2 pi y, it works the same way. And now we can do all of those calculations you did on last week's homework, not the one you just gave me, but the one from before, parametrically. Now y'all are looking at me like I just barfed into your faces. This came first, before all of the stuff we've done so far. The original work in calculus is all done parametrically. Newton's papers, Leibniz's papers, Wallace's papers, Brown's papers, they're all done parametrically. That's the way the physics of the time worked. And they did calculus to solve problems in physics. All of those problems go from being problems in X and Y to being problems in T now. Parametric equations are a hugely powerful tool. They're also not the only coordinate system on my calculator. In order to draw the graphs we were drawing, we went to the mode button, and that second option says PAR, parametric. There are more options. Guess what we're doing after break? Which means I don't see you all until Wednesday next. Have a wonderful extended weekend. I will see you then.